joining my session about natural language processing and chatbots and a little bit of machine learning. So quickly, a little bit about me. I work for Oracle. I'm a solutions architect or consultant working at Oracle, been there for about 5 years. And my core day job, I focus mainly on Oracle technologies. But I've also been studying data science for the last 3 years, mainly through online courses with Coursera and so on. That's mainly R-based, but I'm getting more and more into the Python world, sort of mapping all my learnings in R across to Python. And home life, yeah, married with 2 children, both children learning Python at an early age, you'll be pleased to hear. And my real passion in life is fencing. So I used to compete for Great Britain, and that's still something I spend as much time as I can doing. Okay, so I mean, why are we talking about chatbots? I mean, chatbots were not in my mind 6 months ago, but there just seems to be an extraordinary amount of hype around chatbots at the moment. Not a day goes past where someone doesn't talk to me about chatbots or some new initiative about chatbots. And this is not a real Gartner slide. I saw it on Twitter and I just pinched it because I felt it was quite appropriate, really. And I reckon we're at that peak of inflated expectations, but I'm sure it'll all bottom out, and then we'll end up with some kind of useful applications. So, what are we going to cover today? Well, first of all, I'm going to introduce a very basic working example, which I've called SimpleBot, which doesn't use any natural language processing or machine learning, but it's quite interesting how well that does work. It's just based in Python and a MySQL database, and really that just sets some background, sort of the motivation for getting into natural language processing and why we need a bit of machine learning to do anything useful. And the core of today, I'm just going to walk through 4 Python notebooks. An introduction to the Python NLTK toolkit, using that to tokenize text and extract parts of speech tags, and then starting to look at how we can programmatically analyze the grammar structure of sentences. And then finally, a very simple example of classifying sentences using machine learning. And then the idea is, towards the end, I'm going to pull all this together, show these different concepts and techniques that we've covered into a basic working chatbot, which I've got deployed on a cloud server. And hopefully, well, we'll see how it goes, but hopefully we can all connect to it, try chatting to it, and well, we'll see how it goes. That'll be a bit of an experiment. I would like to set expectations. I think the important point, this talk is broad, not deep. I mean, it was advertised as novice. If you're a long-term user of the NLTK toolkit, and you're probably not going to learn something new. This is all introductory, basic concepts today. But we will achieve something useful at the end. Okay, very quickly, I mean, what do we need for a chatbot server? I mean, we need a system for taking in human chat, natural language, and responding back, not in code or summaries, technical summaries, but responding back with natural language. We're probably going to have some sort of API interface, web page, messenger APIs like Facebook is one people commonly use, Slack and so on. And the core of this, we need a server receiving all those different inputs and outputs, a repository of knowledge that it can refer to, and a method of parsing that language that's coming into it and responding back in a sensible way. So we're probably going to need some sort of machine learning to help us with that, and we'll need some sort of knowledge base in our chatbot server, i.e. a database. So I'm just focusing on the chatbot server part. As you will see shortly, I've put no effort, time or thought into the sort of input API. I've got like a simple TCP sockets client, just so we can get multiple people connected to it. So on the basis of that, what did I do? I started by just trying to deconstruct the chatbot server, wrote something in Python with a simple thing running around in a loop with a multi-threaded server concept connecting to a SQL database and some simple command line Python clients connecting into it. And I'll show an example of what that looks like very quickly in a minute. But then the idea was then to sort of build this up a bit, and we'll work through the process of adding in the Python NLTK libraries to process and analyze the language. And also I do a very brief example of using scikit learn to use a random forest model to classify the sentences as they come in, so we work out what type of chat sentence we're dealing with, which is quite interesting, I think. So, yeah, I mean, this is a sort of trivial example, and it's something I stole from someone else. I just found a blog post by a guy called Matthew Roddick, I think, and it's sort of trivial but clever at the same time. And what he did was he just used a database schema and SQL to create a chatbot that gives the impression, well, it does learn. It learns by previous examples, and it just uses a bag of words approach, and based on the chatbot's output and then what the human responds with, it just maps associations from the chatbot server, chatbot sentence, to the words it received back. And from that, it builds up quite a kind of, if you just use basic chat, quite an impressive ability to learn. So the sort of thing that you can do. Failed at the first hurdle. I think I'm not connected to the network, am I? Sorry about this. I may as well do this because lots of other things are not going to work if I'm not connected. Let's try that again. Right. Right, well, you get the idea, and the sort of thing you can do is you could tell it, you could train it to know what is a cat. So, what is a cat? A cat is an animal that, I don't know, what does it do? Chases mice. So now if we say what is a cat, but if we say what is a dog, we get a slightly disappointing response. So for basic kind of trivial chat, that's all looking good, but then obviously we need to process our sentences a bit more intelligently, realizing that we need some real focus on the object of that sentence and so on. So a little bit of a digression there. So what are the sort of problems we need to try and solve? You know, we need to try and identify the general topic of the sentence, just counting words. That, you know, you see a lot of examples processing large bodies of text in Python and other sort of analytical languages, and they focus heavily on the sort of frequency of words and things like that. Well, obviously that's not going to work very well when all we've got is one sentence to deal with. And then you've got things like, take the sentence, the cat is dead, and the sentence, is the cat dead? Exactly the same words, we've just changed the order, and they've got a completely different context. Those are sort of problems that the notebooks we're going to work through and the processes try to solve. And Yes. So we need to dive into natural language processing and focus on what we need to do for managing a sort of human-computer dialogue system. And although I've mainly focused on the Python NLTK, which seems to be the core, most commonly used library for natural language processing, I think there's a lot of other packages out there as well. I think one of particular note is Spacey. If you're not such a problem for chatbots, I'd say, because you tend to be just dealing with small quantities of text at a time. But if you're processing large amounts of data, then you might want something written in C, like Spacey. And also that it does appear to be quite functionally rich as well. And then something that I'm going to introduce later on, I think is a fantastic package, the Stanford Core NLP package, which is written in Java, but there are bindings in NLTK, so it's very easy to use. I see sort of smiles of acknowledgement in the corner. Is that something you're familiar with? Or?
Yes, but not very familiar, just read the docs.
Oh, okay, good, right. Well, so I only scratched the surface of it, but it worked very well for me. So really this is the core of today, and I have to admit I've not done one of these before, because I've tried looking at the format that other people. So I'm not quite sure whether this is just a stand-up talk and present, or whether people are wanting to do this kind of hands-on while I talk. So I'm going to work through some notebooks, cell by cell, and talk through it. But if you want to clone them now, you can. There's the repo, or you can just take a cut later. Does anybody want me to pause while you download them now, or should I carry on? Feedback, welcome. I'll carry on. Okay. So this one I'll try and go through as quickly as possible, because it's kind of really a preamble before we get into the core natural language processing that we need for chatbots. So generally, when people are talking about natural language processing, they always start from the point of a corpus and tree banks, and all a corpus is just a very large body of text to develop your natural language processing models around. So I think that the most frequently referred to one that I found is the Brown corpus from Brown University. And these different corpuses, they tend to have different levels of annotation and sort of semantic detail, or annotated against them, depending on how much research has been done with it. And taking that a step further, we come to a tree bank, which is parsed and annotated so that for every sentence and hopefully word in the body of text, we've got features and classifications identified in it. So there's a lot of different corpuses, corpora, and tree banks that bundled with the NLTK, which is very convenient. They don't all come down all downloaded, because they just take up too much space, so you have to download the ones you want, and it's got a very kind of user-friendly way of handling that using the NLTK download function. So there's one very good one, is the Reuters corpus, which I think is all the Newswire articles from 1987. Didn't think of making a note of that. Oh well. And so I've already got mine downloaded. And each of these with each of these corpuses, there's various functions we can apply against them. So for instance, we can look at all the files that make it up, or more interestingly, we can look at categories that have been set in the text by whoever created this corpus. And we can extract words and sentences from them. So if I just do a quick example. So before that, there's a few more. There's various standard utilities in the form of corpora that you get, or data sets that you get from the NLTK. And one of these is punct, which is a way of tokenizing by punctuation as a part of speech tagger. And there's also a list of stop words, which are just useful tools that we'll refer to later. So here's an example with the Reuters corpus. So I can start by just looking at what categories have been used to classify the text. And so there's 90 different categories, and I've just taken the first 10 and last 10 sample. So you can see that they've classified newswire articles by do they reference barley, trade, wheat, and so on. So if you're doing bulk text processing and analysis, that could be useful. You could look at, so here, oops. So here's an example. We might want to just say extract all the newswire articles that cover the category trade. Sorry, all the words. And then the sort of processing people might do is then just you want to remove all the stop words, and then this will take a while because of my very inefficient coding. I'm going through the entire 142,000 words and iterating through it and ripping out all those stop words. Give it a couple of minutes and it'll be there. While that's running, all we're going to do is use a simple frequency distribution tool that comes with NLTK, and we can look at what are the most common words in the documents that are classified under trade, and we can also look at things like bigrams, what are the most common word pairs. Still running. So this is kind of a preamble before we get into the kind of core useful tools that we're going to use for chatbot processing. But having a large corpus of text obviously is very useful for training a model, especially if the classification happens to match the topic areas that you want to classify your text by. But it's kind of, it depends whether one's ready and available for you. Otherwise, you're going to have to classify your own. And what we'll see later on is I just generated my own set of text with my own classifications to suit my own requirements. Right, good, that's finished. So having stripped out all the stop words, whatever, we're down to about, what we're hoping is a representative set of meaningful words in our text. And this is not supposed to take a long time, so I'm not sure. Right. So here we can see that the top 20 most common words in that text that classified as trade. We've got things like billion, Japan, Japanese, surplus, deficit. So you can see people who want to build models to work out is this document likely to be about, is this newswire article likely to be about trade? You could do that very easily with sort of distributions of commonly occurring word counts, and if you can do things like bigrams and skipgrams as well. And I think in the field of sort of e-discovery and text, document retrieval, this is the sort of thing people are doing. So in these articles about trade, here we're seeing the bigrams are even more telling. Trade surplus, trade deficit, United States. So you could quite easily build a system for giving a probability of a document being related to trade. Yes, please. Yeah.
I was wondering for the categories and everything, like is that a Reuters corpus specific thing?
Yes. So yeah, that is the challenge. So you need to find. There's I've referenced it in this notebook. Don't know what happened there. I've put a few links in here, so you'll probably find the notebook's more useful for the links and references than my clumsy coding style. But yeah, if we have a look at that, you'll see here are the corpora that you get with a natural language toolkit. There's a lot of them, and it's a bit of a voyage of discovery, trying to find out one that's useful for your needs. So, before we move on, I'll just very quickly have a look at a tree bank. So this is the Penn tree bank, where you get a 10% sample of that with the natural language toolkit, which is plenty. And if I extract the words from that, and then what I've done here is I've just looked at, say, the first 10 words. You can see each word, the first word, Pierre, and then it's being tagged with a classification, NNP, for personal pronoun. And then his surname, also personal pronoun. 61, CD, years, NNS, and that tag just means it's a plural noun, and so on, old as an adjective. So every single word in that tree bank has been classified in that way. And you can also extract by sentence. And you can see in this tree bank what they've done is they've also defined a sort of a tree structure. So, which must have been a kind of a momentous piece of work to do this, but you can, out of this, if you wanted to develop, analysis of the different structures of languages, you've got something to work against. So here we've got the sort of root of the tree, S for sentence, and then we'll talk about what some of these things mean later, but NP for a noun phrase, VP for a verb phrase, and that noun phrase is identified as the subject made up of this guy's name and so on and so on. So I don't want to spend too much time on this, but other than just introducing the concepts, the vocabulary, and points of reference if you want to look at it in more detail. And this is very useful when I was trying to debug my slightly brain dead chatbot and get it to work a little bit better. Being able to visualize the structure of the grammar like this I found very useful. So you can just take that parsed sentence and in IPython, in Jupyter, you display it this way, and then there's an equivalent method if you're not using Jupyter, but that comes bundled with an NLTK. Right, so that's a very kind of quick whistle-stop tour of what a corpus is and a tree bank. Any questions on that before we move on to the core topic, which is tokenizing and tagging text? Okay. So, all those techniques, that's great for kind of large volumes of data, but if we've just got a sentence coming into our chatbot and we want to decide how to respond to it appropriately, we need to look at things in a bit more of a granular way. So first of all, we need to break up our text into sentences. And then within that, we'll need to break up that sentence into individual words, and we'll probably need to have some kind of understanding of relationships between those words if we're going to go beyond just sort of counting the frequency and occurrence of actual English words. So this is generally known as part of speech or POS tagging. So there's several different ways of tokenizing text in general, and there's several different tokenizers bundled with the NLTK. The default one is called the punced sentence tokenizer. And so what I've done here is I've just taken some text from Ulysses, because it's kind of an interestingly non-trivial, non-simple set of English text. Don't know why I've used escape line feeds on the end. Sorry about that. Anyway, it works. So let's just have a look at what that looks like if we try and use the sentence tokenizer to split it up into sentences. So here I've broken it out line by line, and you see it's quite easily confused. So I guess James Joyce is using a exclamation mark not as the end of a sentence there, which I think is valid. I'm not an English language expert. And similarly, any kind of exclamations or dashes like that confuses it. So we get our sentences split up in a way that would probably really confuse a chatbot. So this is just to kind of like illustrate some of the challenges we have when you get into the real world. So even in that very simple example, we can see things going off. So there's many ways of tokenizing text into words. I didn't look at them all, but I've just focused on the ones that seem to be most commonly referenced. And what I've done here is I've chosen 3 different tokenizers. So the default tokenizer that NLTK uses based on the pen tree bank, which we saw briefly earlier. There's also the word punced tokenizer, which, as you can probably guess, just uses punctuation. And then there's the space tokenizer, which tokenizes on white space. And instinctively, white space would seem to be a good way to go to me, but actually, by kind of my experiments, I'd say that the default NLTK tokenizer is probably based on the pen tree bank. It's probably the best way to go. So if we just take a simple sentence like, Mary had a little lamb, its fleece was white as snow. Even with that single sentence, we get 3 different outcomes. So for the default tokenizer, we've got it and S has been split apart. The punced tokenizer has split it apart as well, but it's moved the apostrophe off, and that's been identified as a token in its own right. And then finally, the space tokenizer, obviously because it just works on blank space, has kept its all as one item. So that has an impact. So as well as splitting into tokens, we need to identify the parts of speech for each token that we've got. And that's all nicely handled for us with the POS tagger. So if we take the tokens that are generated with the default tree bank tokenizer, which I've stored in tree tokens, and we also look at the space tokens, and we look at the effect that has, we can see that for the default NLTK tokenizer, it has been identified as a PRP, personal pronoun, S as a verb, which I think that's correct. If you use the space tokenizer, it is considered to be a noun, which is not correct. So I guess that's just a little illustration of why kind of I started by just splitting everything up using spaces, and that can go off course. So all these different tags, I've just pasted them into this notebook for reference, and obviously I'm not going to go through them all, but you get the idea. Just about every part of speech you can think of is classified, and also the way they've done it, all the different types of noun start with an N, all the different versions of verbs start with a V, which is good if you want to do quick and dirty hacks with regular expressions, which is kind of my general way of working. It works quite nicely. So yeah, if we take the Mary had a little lamb sentence, we've now tokenized it, and we can just extract all the nouns out of that sentence. Mary lamb, please. So although that's very simple, we've moved on a great deal from just looking at a bag of words that are all equally valid. We can say actually we want to pick out the nouns, give those extra weighting in our consideration. Right, so this bit, stemming and lemmatizing, I'm covering it because it seems to be a kind of a core part of the domain. I have to say, I got very little practical benefit from it, and it might be just because I was doing it wrong. But this is the topic of just stripping words down to their, either taking the suffixes off, so trying to identify the core word, or trying to map that word back to a kind of a core dictionary definition. And I think you can sort of see instinctively or intuitively why that would be a very useful thing to do. And I think the challenge is that, well, the tools that I tried just didn't work very well. So I got very indeterminate, got very kind of variable results with it, inexact, I think that's the best way. So there's three kind of stemming methods generally referenced. The Porter stemmer, which I think was the original NLTK stemmer. Something called the Lancaster stemmer, developed at the University of Lancaster. And then the snowball stemmer, which is what, from what I can gather on Stack Overflow and so on, is what most people seem to be using. And that's just the next iteration of the Porter stemmer. So I think the best way to explain it is just look at a quick example. So if I've got three stemmers, the Porter, the Lancaster, the snowball, and I don't know where I got this sentence from, but here's a sentence that has some interesting aspects for classification. So if we look at the stemmed version of those two sentences using those three different stemming methods, we get very variable results. So for instance, only the Lancaster stemmer has left Mary as Mary. The others have changed her name, which could cause problems. One of them has changed was to WA. And ideally, the sort of useful thing this could do would be to change lying. You might want, as in the root of that would be lie. But so here, the snowball stemmer had a pretty good go at when I was going to the woods. So it's changed going to go. It's changed lying to lie. So I'll take it back. I'd say the snowball stemmer does work reasonably effectively. But in other examples, which I don't seem to have recorded here, well, for instance here, how it's dealing with personal pronouns, changing people's names is not convenient. Could cause problems. So lemmatization, similar sort of idea, but it's trying to refer back to base dictionary words. And here's those two sentences processed using the WordNet lemmatizer. And again, it's okay, but there are some odd variations in it. And I didn't really use stemming, or I started off assuming that would be the best way to go, but I found it difficult to get anything that was dependable with it. So I've left, I'm rushing through these because I want to kind of get to the end, a complete package, something that can be used, but I've left on these. I did quite a lot of other stuff other than what I'm showing in these notebooks, and I've just left some. The only really way to get into it is to play around, experiment, mess about, and I've just left, you know, my 2 pence worth tagged on the bottom of these notebooks for ideas to explore. But just in summary, you know, where we've got to now, so now we can tokenize text into sentences. We can go beyond counting the frequency of actual words and classify words by a type, and so we can identify features in the text. So, and that part seems to be the core bread and butter of what we need for a chatbot. But if we want to get a bit more sophisticated, we need to look at the grammar structure of a sentence. So not just, is this a noun, is this a verb, is this a personal pronoun, but you know, what are the important nouns and what are the relationships of those nouns? So what's the object of this sentence? What's the subject? Who's performing the action? What's the topic? And that is a much more tricky thing to do. So I started looking at what was available in the natural language toolkit, and it's got this thing it refers to as the CFG class, which stands for config grammar, I think. Now, this is just taken straight out of the NLTK book. So actually, I should have, before starting this, I should have introduced that there's something called the NLTK book. If you're interested in this, I mean, that is a fantastic resource, and that's the starting point, I would say, is using the NLTK book. There's worked examples, yeah, and all of these topics I'm covering are, or most of these topics I'm covering are in there. But in some cases, I've had to kind of extend beyond the NLTK book, as we'll see. So anyway, this is what you get in the NLTK book, and basically you build your own kind of method of parsing grammar in a text string like this. This is their example, and so the root is identified as S, and what they're saying here is that our root S, the whole sentence, can be made up of noun phrases and verb phrases. That's the first rule. And then here we're saying that, you know, noun phrases can be built up out of determinate nouns or determinate nouns with, can't remember what PP is, prepositions, I think, and so on. So sort of manually building up your rules in a text string like this, which I guess you could extract from one of the tree banks, but unless I've missed it, that hasn't been done. And then mapping the words in the sentence you want to analyze back to some pos tags. So that, well, let's just see what that looks like before we talk about what it gives me. The best thing about this is the sentence, in my opinion, which is, I shot an elephant in my pajamas, which is an interesting conundrum. And so if we create this grammar, and then we try using the parser for that grammar against that sentence, we'll see that we actually get 2 grammar trees coming back, because it's not possible for it to tell whether the elephant was wearing the pajamas or the person doing the shooting was wearing the pajamas. But that's all very good, and also you can draw a nice little chart of that sort of graph relationship. So the observation made in the NLTK book is that it's very hard to scale this approach up for any large texts, and I'd agree with that. And I was in the market for not writing my own from scratch. I was looking for useful tools to make this easy for me. And after looking around for quite a bit and toying with various things, I fell upon the Stanford NLP, Core NLP software package, which is brilliant, and it's a huge topic. I've only scratched the surface of it. It's very well documented, but it seems to be very well supported. And the best thing of all, there's bindings in Python NLTK, so you can reference the Stanford parser directly from within NLTK. So, and I would say if you're going to be getting into grammar parsing, take a look at it. So, to get that to work, there's a little bit of setup involved, and that's where we get into some dependencies if you want to try running these notebooks yourself. So the first thing is you'll need Java 8 installed, and also you'll need the Stanford Core NLP package installed in the form of a couple of jar files. And so then what I'm doing here is first of all just import the binding to the Stanford dependency parser, and then I'm setting up a path to the jar files, and then you can initialize it like this, just referencing the telling it where its jar files are, basically. So, without any of that effort that we had to go through for the NLTK version, if I just call the Stanford dependency parser, pass in this sentence, it returns a result, which you then have to just take the next item off. Then what it gives you, there we go, good. What it gives you is you can iterate through a set of triples, which is really nice, I think. So here, so each of these triple, we've got sort of a root and an association or relationship to a branch. So here it's saying I is related to shot as being the subject, and elephant is related to shot as being an object. I mean, and that, I mean, for me, we're in a whole other world now of sophistication in terms of language processing, I'd say, being able to do that. And, you know, from that point on, you know, where you take that is kind of, you may not go the same direction as me. I think I haven't really explored how far you can go a long way once you've got that ability to analyze and process programmatically the structure of the language and the relationships of the words in that sentence. You can be quite targeted. So some of these relationship definitions are kind of obvious. That's obviously a noun subject, that's an object. Some of them are less obvious. They're all documented here. And this appears to be a collaboration between Google and Stanford University. And so they explain what all these different dependency relations mean. So, where am I? So, does anybody have any questions they want to ask before I also need to check how long have I got? 5-0, fine. Okay, I thought you said 1. Right, good. Okay, so the most useful thing of all, we can just find out what the root word is in a sentence. So in that case, it's shot. So, you know, outside the field of chatbots, that means now we can very easily, sentence by sentence, say what's the topic of that sentence. It's about shooting. So, and we can extract the tree in sort of a list format like that, and we can look at it as a little graph. As well, which is very useful for when you're trying to analyze more kind of complex sentences and debug why your particular text processing algorithm is not working very well. So if we take a much more kind of complicated sentence, again going back to that Ulysses text, I mean that is a real mental sort of tongue twister, whatever. He watched the dark eye slits narrowing with greed till her eyes were green stones. It's very, very poetic, but it does a very good job of picking that apart and understanding the structure. So it decides that the head word is watched, so that's the topic, and I think that seems correct to me. And then here's the dependency graph. So he watched, and then there's narrowing, but with these modifiers, the dark eye slits, and he watched with greed, and then we've got the object eyes, her eyes, and then the only bit that's slightly confusing is it thinks he watched stones when in fact he watched her eyes. But that's a pretty accurate deconstruction of quite a complex sentence. So if we kind of modify our sentence, I shot an elephant, and we just make it a bit more specific, while I was wearing pajamas, then yeah, we get a nice I shot, object, an elephant, and then there's this kind of modifier, while I was wearing pajamas, has been separated off. So that works very well. I mean, I've come up with this sort of toy example here, a very simple algorithm for based on that. So just, what are the most interesting things we could know on a sentence by sentence basis? What's the core topic? What's the subject? And what's the object? So I'm sure it's a lot of code. I'm sure many of you could do a better job than me, but here's the sort of an example of the sort of thing you could do. Kind of a bunch of random sentences plucked from my mind, varying from Ulysses to Oracle product release information. I mean, this is a difficult sentence. PyData community gathers to discuss how best to apply languages and tools to continuously evolving challenges in... We've gone off the screen, but I picked that off the PyData website. And a couple of thoughts on Arsenal. So if we run that through this little bit of code, which just like passes through the triples for each of those sentences and extracts out the topics, subjects and objects. You can see for the first one we've already seen this. It's worked out the subject is he, topic is watched, object narrowing eye slits. So when will the Oracle 12.2 database be released? It's worked out that the topic is about release and the subject is database. Coherence is about clustering, which is correct, and the topic subject. So you can see that works. Even though it was a bit of a crude approach I took, it actually works quite effectively if you just want to take a sentence and say, well, boil it down. What's this sentence about? What's the subject? What's the object? When will Arsenal ever win a match? Well, the topic is winning, the subject is Arsenal, the object is match. That's pretty good. So, this gives us a way to programmatically analyze sentences, looking at their grammar structure, pick out a topic, and classify. And we can also classify groups of words based on how they relate to each other in the sentence. So I'm sure that hopefully it'll be an interesting task to take away. Look at my little toy example, use the Stanford dependency parser, and I think there's quite a lot of mileage in that. Okay, so is this sort of kind of interesting and relevant? Is this at the right level, people? Okay, good, right. I've never presented at an event like this as well, so I'm just interested in whether I'm kind of at the right level, covering the right sort of stuff. That's good. Okay. Right. So given that, there's one aspect that we haven't really covered, and that is the sort of the flow in the chatbot. So what I didn't really demonstrate at the beginning when I showed us talking to that little chatbot server is the challenge of, if you ask the chatbot a question, you want it to give you an answer. Similarly, if you tell it a piece of information, you don't necessarily want it to chat back, you just want it to store it. I've taken the example of what if we could use the chatbot to become a simple sort of FAQ server. So it either stores pieces of information or it responds to queries. And then thirdly, because I kind of mocked this up and launched it on my long-suffering colleagues and had them all working with this chatbot server, the other thing I've noticed is that it doesn't matter how much you tell people this is just a chatbot server, it's very, very simple, all it does is this. People start chatting to it. And because I was working with the database, I could see what people are saying, and they're like going, "Hey, how's it going, man?" And "Are you a bot?" and "What's the weather like?" and stuff like that. And so the chatbot needs to be able to not only deconstruct the sentence in the way we've just been talking through, it also needs to be able to work out what type of sentence is there. So, I mean, that's a big topic, a big problem, and so I boiled that down into something that's kind of manageable for presentation. And if we can just work out, is a sentence a question, is it a statement, or is it anything else really, chat, let's say, then that would be very useful. So that brings me on to the sort of final Python notebook I'd like to work through. So here I kind of, until now really, I've just been taking excerpts out of what's already in various very good sort of comprehensive bits of documentation, whether it's the Stanford NLP library or the NLTK docs or other blogs and so on. Here I sort of spin off slightly into my own crazy world of my own approach of using generating features from sentences so that we can apply a machine learning model to it. And the focus of this, although I use random forest for this, the focus of this is more a strategy for generating features so that we can do something useful, and that seems to be the challenge here when dealing with just a bunch of text. So the process we need to go through is in this notebook is we load some data in, and that data is pre-classified, so this is supervised learning. So I've taken 100 sentences that I think were mainly just typed in by colleagues when we were messing around with this thing, and each sentence I've classified with a C for chat, a Q for question, and S for statement. And then it's how to come up with a method of extracting features from that data so that we can build an effective, we can use a machine learning algorithm to build some sort of model for classifying other sentences. And then we'll do that. We'll build a model against the training data set, validate it, and then we'll test out and see how successful that is. So to do this notebook's dependent on some other data. So there's sentences.csv. So I've just supplied the link to that in this notebook. Or you can once you see the structure, you can do your own. Also, to do some of the validation, I've taken some statements from the Python FAQ. So if you want to follow this notebook kind of line by line, then you'd have to download that CSV as well. And then most importantly of all, there's this features Python module that I've written, which basically does a huge amount of grunt work, just processing the sentences and then extracting the features in the method I'm just going to using the method I'm just going to describe in a minute. So you can either, if you clone this GitHub repo, then you get the whole lot bundled in with it, as well as my ChatBot code. Or you can, I put them as a release in GitHub as well, so you can just pull the individual CSVs if you want. Right, so let's just go through it step by step. So we'll load my sentences data and pull it into a pandas data frame. And so if you were doing this, you'd need to, I haven't done anything kind of clever like a requests get or anything like this. It's literally get the CSV, put it somewhere local on your laptop, and load it in and set the path appropriately. So I've loaded that data in. If we just look at the first few lines, 11 lines. So, sorry, I don't know about the weather, a statement. That is a tricky question to answer. Chat. Some of these classifications are a bit dubious, I'll say, done in a hurry by me, but some of them are pretty clear cut. If you deploy a MySQL database in the Oracle, don't know what the rest of the sentence is, that's a question. And this is clearly a statement. Max is a mobile application accelerator. Well, that's clearly not put in by me. That's an Oracle product. I've got no idea what that is, even after reading that sentence. But so that's the structure of the data set we're starting from. There's 100 of those. Just in that sentence class format. So chapter 6 of the NLTK book has some great kind of worked examples of how to do things like naive Bayes classification and so on. And I suggest just take a look in the NLTK book and work through the examples. So what I'm going to do is something a little bit more weird and wonderful, and I'll, kind of polite feedback afterwards, whether you think it works or not. Be interested in what you have to say about it. It appears to work technically, at least. So this is going to be, I was thinking how to explain this clearly. So what I've got here is a little sort of sample bit of code where I take in a sentence, can a dog see in colour? I don't know why. And then I tokenize it, and let's just print out the tags that we get for that. So can MD A DT, and then if I just throw away the words and just extract out the tags MD, then that sentence turns into just a string of pos tags MD DT NN NN IN NN. So we've got some features, but then what I did is I experimented with breaking it up into sequences of triples. So the first triple is MD DT NN. The second triple starts here, DT NN NN. And hopefully you get the idea. And there's all sorts of variations of that technique that you can do to just build up secret patterns that you can then count for a given sentence, and then by counting those we've then got some numeric features we can work with. So what I did was I just ran that through and bulk processed all my sentences and extracted all the triples for each sentence. I've just wrapped all that kind of grunt work as I described into a utility called features, and basically you pass in a sentence and it spits out a dictionary of the features it's identified. So buried within that is all sorts of stuff. The most important one really is get triples. which returns a string like that. And yeah, there's an example of it. What it would do, you pass in can a dog see in colour and it returns out that. So if I run that through all the sentences in my data set, I get quite a lot of data to process. And then what I did is I just loaded it all into a SQL database. So I've got 360 different triples to deal with. But each triple, each row observation in the data table also had the classifier C, Q, or S. So here's the kind of the breakdown. The chat, not very fruitful for triples, but I've got a good, reasonably good spread between question and statements for the numbers of triple items in the database. But then what's more interesting is we'll then write a query to break it out into groups. So this query is saying that there are, I'm not going to run the query live, but there are 5 occurrences of that triple pattern, and we only have them for question statements. That's quite useful. 3 occurrences of that triple sequence, they only occur in sentence statements. And these ones I've just manually highlighted them in HTML to just try and explain it in this talk. So these ones highlighted in grey, yeah, we've got 3 DT, NN, NNs classified as Q, but we've also got some as S. So they're not very useful. So out of that, I was able to identify sort of 10 sets of triples that were common identifiers for questions and 10 or so that were common identifiers for statements. And I kind of evolved this technique a bit. Sure.
Just on those, that's not position dependent, is it? That's just within any given sentence that structure occurs, rather than it occurring at the beginning and the end.
Correct. So,
Can you repeat the question?
yeah, so the question was the counting of this occurrence of triples is not specific to being at the beginning or the end. And correct, in this example, it's just, does that pattern occur in the sentence? Simple as that. I didn't just do this on those features. I also did the main exercise was I was trying to do classification without any word count. So the rule I set myself is I'm not going to count question words like where, is, why, because it just seems to be a flawed approach to me, But then, all these things, it's a mixture of, science, alchemy, guesswork, and luck in the end. And I think if I kind of step back from this kind of artificial exercise of just trying to do it with triple patterns, then I think the kind of algorithm, the approach I've taken will go up from being about 85% accurate to possibly 95, But this is a kind of just one technique I'm trying to illustrate, if that makes sense. So the most fruitful methods were the triples, and also I cheated a bit just to make it a bit more accurate. I cheated does a verb occur before a noun in a sentence? Quite easy. So sentences that have a verb before a noun, I think they tend to be questions. Yeah. Is that general? So hopefully you can see roughly what I'm doing. So just carrying that on, I ended up coming up with like my bespoke features generator. So when I put in some sentences like that, so can a dog see in colour actually fails on my triple score, so it gets a score of 0. And for the statement score, which I've called S triple score, it also gets a triple score of 0. So that hasn't worked on the triples. But we're lucky in this case, there's a question mark on the end. So I do count, that's probably my biggest cheat in this whole thing, I do count question marks, but this method does pick up questions that don't have a question. So I'll do a demo later. But we've also got some other things here like Q-verb combo. I think there's some, like, as well as triples, I count doubles as well. There's some other combinations that also help. So just take that approach and multiply it out for about 10 different features is what I've done. But I don't want to go through it one by one. So that was a lot of work. I mean, I think that was about a week's worth of hacking and messing about and generating some features. When all said and done, basically I've got a little Python script that will just read in sentences. I just hash the sentence itself, just so I've got a unique identifier, which is useful to have. And then a whole bunch of numeric features and a classification on the end. So, so that I've done this in advance. I've got something called features dump, which is basically taking the sentences.csv, running it through my features extractor, dumping it out into CSV. So working with that features dump, let's load it in. I split it into a test and training data set. So I've got a random 75 rows from my sentences in my training set and 25 in my test set. And then, yeah, it was like a week's worth of trying to extract some features and about, I think, half an hour on the train to build a model and test it, and it was easy. So I used random forest, not a huge amount of science in how I chose random forest other than past experience, and it's a classification problem, and yeah, and it was easy. So I've built my random forest classifier. So if I try predicting from my test set, let's just, so yeah, I've just taken my test set, run a prediction with my random forest model. If I look at what I've got in my prediction output, we'll look at this properly in a second in a confusion matrix. You can see actual statement, predicted statement, this sentence ID, predicted statement, actual statement, and then there's a few that are wrong, like that one, and you'd have to map back using the hash ID to work out what the sentence was. So if I do some kind of very basic validation using Panda's crosstab, I can print out a little confusion matrix, and that looks pretty good. It's well, it depends on your definition of good. I mean, I cut quite a few shortcuts with this, and I'd say the training data set wasn't ideal in a lot of ways, and still got about 90% accuracy in terms of the prediction, as in was it a statement, was it a question, was it chat. And you know, if you design your flow of your chatbot appropriately, that's probably good enough, because you know, you can have built into it, as you'll see I have in a minute, you know, if it gets a statement, it says, would you like me to store that for you? You could you could always say no, and then it'll then you can try putting what you want to say in again in a clearer way, and it will get it. I would say that I mean, there are some flaws. I have been studying data science with Coursera for 3 years. I think there are quite a few kind of flaws and shortcuts in my approach. Not least is the fact that I've developed my strategy for the features against quite a small data set, and then and then use that same data set for testing against. So just to kind of make it a bit more challenging, I just went to the Python FAQ website, and I'd never read it actually. I'd never read it until this, and I tried putting in statements from the FAQ and questions from the FAQ into another CSV to see how my model worked predicting against that. I also added some random statements like, what do you reckon, yeah, whatever. If maybe I should show the CSV that I load in just to make it. So first question on the FAQ, what is Python? Python is an interpreted object-oriented programming language. So that's all I've done. And then I've loaded a load of chat things in to make it more difficult for it, because chat is challenging. Right. So, how do we do? So basically I load in all my features and then use the model that we built previously and cross-check the prediction, cross-check the accuracy, and not so good. But it still works. Right. So, I mean, so the accuracy for chat is pretty low, but it's picking it's getting questions and statements correct about 80% of the time. So, not bad, but I thought it was also important to kind of illustrate the limitations, and I'm quite confident that this could be improved upon quite a lot. This is really a first cut, and I just wanted to sort of illustrate the method and the approach. Maybe this is a standard way of doing things, but I hadn't seen anyone really talking about it, so I thought I'd add it into the talk. Okay, so that's the end of. Oh, so yeah, we could do some ad hoc testing. So if anybody wants to give me a sentence, we'll see if we can classify it. Ideally a statement or a question about anything. A fact.
What is your name?
That is tricky. Do you want a question mark on it or not?
Just like both.
Pardon?
Just like both. With and without question mark.
Okay. Yes, yes. So prediction is question. Right. So right. So, and it's peculiar because when I run it through that sort of validation method I went through, it doesn't, the accuracy doesn't look very good. But I presented this to kind of a smaller group a few months ago, and I was a bit skeptical. And sitting in the pub, people trying to make it go wrong, and people found it frustratingly difficult to make it go wrong. So I'd summarise it as not bad. So I've actually forgotten. I've actually missed out quite a lot of my talk. I've lost my place. Where are we? Classification. Yeah, okay, so given all that, putting it all together, I had a go at constructing a simple FAQ chatbot. using the sort of framework that I've described earlier. And really this just takes some human input and decides, am I dealing with a statement, a question, or chat? If it's a statement, then I use the Stanford NLP parser to extract the topic, the subject, and the object, as well as just the bag of words, and store it, but store it appropriately so the words for that statement are classified in a database table. If it's a question, then I go and look for, then first of all I extract the topic for the question, and then I can go and search from previously stored statements based on those topics mainly, and subjects and objects. And then finally, if it's chat, I can kind of revert back to that example I showed earlier, where it doesn't try to find a statement of fact. So if you just say something inane to it, it doesn't try and tell you about the thinking behind Python or the next Oracle database release date. It just spits some chat back at you. And this works, I mean, this is a complex area, and this works to an extent. I can see lots of flaws in it, and I can also sort of see how I could possibly fix them. But as a starting point, I mean, I think, and I don't know what people think in the room, as a starting point, I think that's a kind of a good summary of the different pieces that you need to put together to make a useful chatbot, i.e. you need to classify the type of statement that you're dealing with, and then if you're storing that, you need to classify it not just in terms of what type of word is this, but also its context in the sentence that it occurred in. And similarly, when you retrieve information, you need to do that. So I've not even considered attempting natural language generation. That looks like a hugely challenging thing to do. It's a lot, and it's amazing how much, if you've got, say, 10 colleagues in your workplace typing stuff, it's amazing how much natural language just builds up in the system anyway. It's a lot easier to just try and spit back something else that someone already put in. But, you know, if you've got like 100 data scientists working on it or whatever, then you could, you know, using the mechanisms I think that are there in the Stanford NLP core package and some much cleverer machine learning algorithms than the ones I've been using, it's possible. So, you know, how did that go? So on my GitHub page in the README, which I've lost, I've kind of got a pre-canned example which shows kind of how well it works and what it looks like when it doesn't work very well. Where is it? Here we go. So here we go. I say hi, it says hello. The latest Python source distribution, yada, yada, yada. Shall I store that as a fact? Yes, thanks, I made a note of it. Here's another fact. Right, so I say here, I say there is a Python news group, etc., etc. So it stores that. Now I say, where can I get the latest Python source code from? Can't find an answer to that, because at the end of the day, we're still doing searches on words for retrieving the statements in answer to questions. So when I answer the question in a different way, where is the latest Python source distribution, then it tells me. So that, yeah, works to an extent, and you know, I can see there's various ways that could be evolved, either by just storing questions it couldn't answer, and then you could get it to ask people that are knowledgeable on that topic the answer for its questions. Or you could like go down the route of storing associated words and mapping those across. It's quite a complicated thing to do. So finally, I think if people are interested, I've got a I've got this ChatBot server running on a little 4 CPU Oracle Cloud VM. We could all connect up to it. Maybe as an experiment, everybody could try and put in 2 or 3 statements, things you've learnt today, and you can try asking back. If everybody did that, you could try, first of all, asking back your own question, to try and retrieve your own statement back again. And then you could try asking something else back. And if there's enough kind of volume of input, maybe it'll be interesting. Or maybe it'll just crash my VM. We'll see. So I'll put some details up on how to do that. I pre-created a slide. Why did I do it like that? So, unfortunately, I've lost the notes with the IP address. So, you have to bear with me a second. Right, so if anybody's going to do this, could you make a note of that IP address before I change screens and do something else? Have we got anywhere to write?
You can paste it in a Word document in digital fonts. It's not visible.
It's not visible, okay. That's a better idea. So there's no authentication. It's a server listening on port 999, and to access it you need I should explain one of the reasons I'm a little bit chaotic is my laptop failed last night and I was up till 1 AM reconstructing things. I've lost track of a few files. So it's probably easier than just copying that URL down. If you just go to that GitHub repo and look in there, there's a file called simpleclient.py in the releases. If you download that, then you can attach to ignore the you can attach the chatbot by going simpleclient.py, then -a for the host address 141.144.33.19, and -p for the port 3 nines. And there we go. If anybody gets connected to it, please tell me, because then I'll know it's working. I can't do it myself, because you won't be able to see my screen. Oh, good. connected? Or?
It says connected. So
Oh, great. So now just say hello.
I did, and it didn't do anything.
Oh, that's not very good then.
Maybe being rude. I don't know.
Ah. No, that's right. Well, let's see if it works for me. Oh, I don't believe it. It's not working. How long have we got? Yeah, yeah. How long have we got till the?
Just a few minutes, 7-8 minutes.
Um,
They're setting up for lunch, right?
Are they? Okay. Well,
If you try port 991, it works.
yeah. So pit 9991 is this, what I call dumb bot.
Oh.
Well, you can mess around with 9991 and you can see what a chatbot with no.
It responds.
Yeah. And in the meantime, I'll see if I can work out what's wrong.
I think it's back on.
Okay.
Really? Wonder what that was then.
Sorry.
That was a disappointing.
No, it didn't.
Oh, maybe Bloomberg is blocking the socket connection.
Yeah. I'm sure I tried it literally an hour ago. It was. I can see lots of people trying to attach. Hmm. Yeah. Okay, well, I'm sorry about that. That does appear to be the curse of the live demo. One works, one doesn't.
Or maybe it's not scaling.
I doubt it, but yeah, it's possible. It's possible.
Or like
These might be using frames here to like essentially
Hmm.
You can share the material on the side
Yeah,
anyway.
yeah, okay. Well, I better stop it there. So I say thank you very much, guys. Sorry, it's slightly a flat ending. I will still be. Thank you.